Welcome to the third part about uncertainty propagation. In this video I will discuss correlations in more detail. Let's recall the uncorrelated case from the previous video. It shows a point cloud of randomly distributed values and the probability distributions along the axis. To motivate correlations, I will introduce a simple example. Let's consider a circuit to determine the value of a resistor. The voltage and the current are measured. The resistance is calculated using Ohm's law. For each measured point, the resistance can now be calculated and drawn as a slope in the diagram. The shown case assumes that voltage and current measurements are uncorrelated. This can be caused either by the intrinsic noise of the measurement instruments or by a fluctuating resistance value. But what happens if the resistor is stable and the measurements are made simultaneously? Then, for example, the voltage could fluctuate, causing the same deviation. But even if the voltage varies, the current will follow according to Ohm's law. This results in a different distribution. Therefore, the resistance can be calculated precisely, even if the measurement values fluctuate. In that case, the measured voltage and the current are correlated. Still, the standard deviation along each axis is the same as before. Correlation can be considered as a hidden variable that predictably influences both measurement quantities. To get a better insight, I will change to 3 dimensions. Now the transfer function to calculate the resistance is shown, and the measurement points can be projected. As expected, correlated measurement values will all result in the same value. Again, the resistance value will scatter more in the case of uncorrelated values. Let's look closer at the point cloud and how the distribution can be modeled. We can use the 2D normal distribution from the uncorrelated case as previously. The calculation of mean and standard deviation from experimental data are as before. The mean and the bounding box of the standard deviation are shown. For the correlated case, one more parameter is required. This parameter can be determined by first calculating the covariance. Note a similar structure between the covariance and the equation for the variance, and remember that the standard deviation is the square root of the variance. A convenient way to express the strength of the correlation is by using the correlation coefficient, which can be calculated using the given equation. The modified equation for the 2D normal distribution is given as well. Again, the loci with equal probability density are described by ellipses. The following shows the ellipses for 1 and 2 sigma. The correlation coefficient can be between -1 and 1. -1 describes the anticorrelated case. This is the case if, with increasing value along the x direction, the value decreases along the y direction. The correlation coefficient 0 represents the uncorrelated case, where x and y values are independent, and the value 1 represents the fully correlated case. If the value increases along the x direction, it also increases along the y direction. Note how smooth the ellipse fits into the rectangle of the standard deviation. Also note that the standard deviations are independent of the correlation coefficient. Having the generalized 2D normal distribution, we could use it to propagate the uncertainty. As in the previous part, the linearized function plane is shown and the ellipse is projected. Depending on the correlation coefficient, which defines the shape of the ellipse together with the derivation function, the set elongation is either extended or reduced. This is included in the extended equation for the uncertainty propagation. Note that the covariance can also be used instead of the correlation coefficient. Let's look at some special cases. In the uncorrelated case, the equation structure cannot be further simplified. In the displayed normalized case, the ellipse is a circle and the radius is 1. The standard deviation are also 1, and the slope of the tangents is 1 each. The final calculation gives a value of square root of 2, which is also the value of the steepest slope. One example of an uncorrelated case is measuring with a ruler with random and therefore uncorrelated uncertainty when reading the ruler. Therefore, when measuring twice, the uncertainty will be the root mean square. In the case of full correlation, the equation can be simplified using the binomial equations. Now the terms are directly summed. This can also be explained by using the diagram. The correlation now causes the ellipse to degenerate to a diagonal with a length of square root of 2. Projecting this on the plane where the slope is also square root of 2 results in the value 2. The example in this case is that the ruler has a wrong scale, so measuring twice with the same ruler will cause the final length to be mistaken for the sum of the individual deviations. In the case of anticorrelation, the equation can be simplified again. Now the result is the difference of both terms. In the split case, this results in a value 0. Note that the effect of the correlation on the resulting standard deviation depends also on the orientation of the function plane. The example in this case is that the wrong scaled ruler can still be used to compare for equal lengths. Here the measurements are correlated as the same ill-scaled ruler is used. However, as the difference is calculated, the partial derivatives have opposite signs, which causes the cancellation of the deviation. For real cases, the correlation lies somewhere between.